Hello everyone, my name is Paydar and I'm going to present the paper Automated GUI Layout Refactoring to Improve Monkey Testing of Android Applications. Well, I start my presentation by describing the problem and the main approach that existing works follow to address this problem. Then I introduce the proposed approach and discuss its initial evaluation results, and finally conclude the presentation. So what's the problem this work tries to address? Well, we all know that Android as an operating system and software development platform has highest market share among mobile operating systems, and every day a lot of Android apps are released to the market, to the users. So from the business point of view, the quality of Android apps is a very essential issue, since otherwise the end users very quickly switch to other apps which provide similar functionality. So the problem is that we need effective testing techniques to detect the faults and quality issues in Android apps at the earliest possible time. Monkey testing is one of the techniques that can be used for this purpose, and we see that the official Android SDK has a monkey tool for this purpose. This can be seen as an evidence that from the point of view of Google, monkey testing of Android apps is important. In monkey testing, a stream of pseudo-random events are automatically generated and fired on the application's GUI to see if they result in any crash or runtime error or undesired behavior, like issuing application not responding errors, or what we call ANR errors. So monkey testing is usually used to do crash testing and to detect robustness and responsiveness issues in Android apps. However, there are different experimental evaluations in the literature that acknowledge that the monkey is not as effective as required. Two specific shortcomings in monkey are that monkey has widget obliviousness and state obliviousness. Widget obliviousness means that the monkey does not have specific knowledge about the GUI of the application under test. For example, where are the widgets? And therefore many of the events that the monkey generates are actually useless. Say for example, monkey clicks on an empty space of the GUI where there is no widget, or it clicks on a static widget like an image or static text. This results in no event handler being called and no code being executed in response to that event. So the event is actually useless. Further, the monkey doesn't differentiate between the widgets. Say for example, we have login screen in the app with two buttons, the login button and the exit button. We know that the code behind the login button is much more complex than the code behind the exit button, and so the login button needs to be pressed much more than the exit button during the test. But monkey does not take such information into consideration. And the second problem is that monkey has a state obliviousness. It means that the monkey does not remember the states that are already explored, and it is very probable that it generates events that do not change the state of the program, and therefore the monkey just moves between repeated states, so the program space is not sufficiently explored. So as a problem statement in this paper, our goal has been to improve effectiveness of monkey testing by specifically tackling the widget obliviousness issue. Next, I will have a very quick review of the main approach that is followed in the literature. The main approach in the literature is to try to propose new monkey testing tools, new methods, or new random testing techniques. For instance, by proposing new event generation strategies that outperform the random event generation strategy of the monkey, or by extracting some information about the GUI and using this information for event generation. For instance, EHP directly calls event handlers instead of generating events on the GUI layer, which indirectly calls the event handlers. Sapiens, which its later version is used in Facebook, uses search-based techniques to minimize the test sequence length while trying to maximize the code coverage. And DinoDroid uses improved event generation strategies. And there are some works that try to support a wider range of user events and system events compared to the events that the monkey supports. But our point of view is that all the existing approaches share the implicit assumption that it's only the monkey that is responsible for the fact that monkey testing is not as effective as expected. So we propose a totally new approach based on a new point of view, which is actually the primary novelty of our work. Next, I will introduce the proposed idea and technique. Our idea is that if monkey testing is not effective, not only is the monkey responsible, but also the app. Well, we know that monkey testing is performed through application's GUI, and it's important to note that the GUI is designed to be user-friendly. I mean, to have a good look and feel for the end user. This is why usually the GUI designers do not use all the available GUI space, or they set different buttons to the same size just to have an appealing look and feel for the end user. So the main idea is that GUI is not designed to be appropriate for monkey testing. It's designed to be appropriate for the end user. So it's not monkey friendly, it's user friendly. And so our idea is that we can have a second version of the app specifically prepared for monkey testing. For this, we propose a fully automated technique that refactors a given Android app to create a monkey-friendly version. And this is through automatic refactoring of the application's GUI, while the application's behavior is not changed. So the goal is to change the GUI in such a way that when monkey testing is executed on the refactored version, less events are useless, less events are wasted, and the widgets that the code behind them is more complex are more interacted with by the monkey, so that it is more probable that the bugs are revealed. And this all means that the monkey testing becomes more effective. Here the overall process of our technique is shown. The input is the source code of the AUT, or application under test, and the output is the refactored version of the app. The first step is project analysis, which the source code of the app is analyzed to identify the XML layout files that define the GUI. Then each identified layout file is passed to the next step to be refactored. In the next step, which is layout analysis, the goal is to identify the interactive GUI elements or widgets. These are the elements that either have an associated event handler, or they are input fields that their value is accessed and read in another event handler method. We call such event handler method the accessor method. So the output of this step is the list of interactive elements along with their associated event handlers and accessor methods. So considering the first type of interactive elements, I mean the widgets that have an associated event handler, it's important to note that identifying these elements is challenging, since actually there are different methods or ways for the developer to set the event handler of a widget. Currently we have considered and supported 3 different methods. The first way or method is to set the event handler in the XML layout file where the widget is being declared. In the XML code shown on the right, you see a button widget is defined and its on-click listener is set immediately. To find such interactive elements, we need to just parse the XML layout file, and it's quite easy. In the second method or second way, the widget is defined in the XML layout file, but its event handler is defined separately in the Java source code, where the event handler method is implemented. In this example, you see the onClick annotation is used in the Java source code to say that this method is the onClick listener or onClick handler for a widget which its ID is @btn or @button. To handle such cases, we need both XML parsing and static analysis of Java code of the project. In the third method, event handler is set in the Java code at runtime, so this case is much harder to handle and advanced static analysis is required to find such cases. In this example, you see the button defined in the XML layout and its onClick listener is set in Java code where the button is first retrieved and then its setter method is called to set the onClick listener. The second type of interactive elements are those widgets that there are actually input fields and their value is accessed in some event handler. Here the input text field, which its ID is username, is accessed and its value is read in this method. So this method is an accessor method for the text field widget. After finding the interactive elements and their associated event handlers or accessor methods, the complexity analysis step is performed. Here, for each method associated with an interactive element, a complexity value is computed. This value is intended to show how complex is the code behind that interactive element or widget. As part of the novelty of our technique, we have proposed a new measure for computing the complexity of a given method. Here it is shown that CNPM or complexity of a method M complexity of a method M is computed based on different notions or aspects of complexity. First is the cyclomatic complexity of M, which shows the number of execution paths in M. It is affected by the number of branches, conditional statements in M. But the point is that it's not just cyclomatic complexity and the branches that need to be taken into consideration. Actually, there are different aspects of complexity. So then it's the call complexity. The idea is that a method M might have a low cyclomatic complexity, but it might call other methods implemented in the source code that they are complex. So we need to include complexity of the methods called by M in the complexity of method M. Next is the API complexity. M might call some methods from the Android API. I mean methods that we have not implemented. They are part of the Android API. We just call them, which they use. They may be very complex methods. For example, methods in the database API or network API. So the point is that the more often method M calls such complex methods, the more risky or more complex or error prone is method M. The next aspect is intent complexity, which deals with the notion of intent, which is specifically introduced in Android API. And simply stated, an intent is a mechanism for passing the control to another GUI screen. So if a method M uses intents, the more complex are those target intents, the more complex is M. And finally is async complexity, which deals with asynchronous tasks. If M creates a background thread or a background asynchronous task, the more complex is that thread, the more complex is M. So after the computing the complexity of the methods associated with the interactive elements is the final step, which is layout refactoring. In this step, for each layout file, first we create a backup and then refactor that layout and replace the original layout with the refactored one. The details of the refactoring algorithm is presented in the paper, but simply stated, the layout is divided into two linear layouts, one for the interactive elements and the other one for the non-interactive elements. The first layout stretches to fill all the GUI space, and the GUI space is divided between the interactive elements based on the complexity of their associated event handlers or accessor methods. The second linear layout, which contains the non-interactive elements, is actually invisible, or its size is set to 0. This means that the widgets that the code behind them is more complex, have a greater share or greater part of the GUI space, and those with less complex code are smaller or have smaller size. Next, I briefly discussed the evaluation of the proposed technique. I have implemented this technique as a plugin for the Android Studio IDE, and we have conducted a case study on an application that is called Satrap. It's an app developed for Ferdows University of Mashhad for registering and monitoring driving fines issued in the university campus. It includes many network-related or database-related functionalities, and it has a total of 38 interactive elements with 42 associated methods and a total of 418 methods. To evaluate the technique and to see how our technique improves effectiveness of monkey testing, we have considered two metrics, HC and MC. HC, or hit count, is the number of times a method is executed in response to the events fired by monkey. MC, or method coverage, is the percentage of the methods of application under test that are executed at least once, either directly or indirectly, due to the events generated by the monkey. And this is a procedure we have used for our experiment. First, a monkey testing session is executed on the original version of the AUT, and then the HC and MC metrics are computed. Then our proposed technique is used to generate the refactored version of the app, and then a second monkey testing session is executed with the same seed as the first session, but this time on the refactored version. And then we compute HC and MC values for the second monkey testing session, and finally we analyze how the HC MC values are changed in the second session in comparison to the first one. Here we have provided an example to show the output of our refactoring technique. This is the main screen of the Satrap app we have used for this case study. Here we see the widgets in the screen from top to bottom. There's the application title and version info, which is static text element, so it's not interactive. It has no event handler. Then there's the application logo, which is again a static image, and again it's not interactive. Next, there are 5 buttons. Clearly they are all interactive because they do something special. And finally, there's the copyright info, which again is a non-interactive element. You see that the non-interactive elements have consumed a lot of GUI space, but since they're not interactive, what's the point in having the monkey clicking or interacting with these elements? Further, you see that all the 5 buttons have the same size, regardless of the complexity or error proneness of the code behind them. This means they have the same chance of being clicked by the monkey, regardless of the complexity of their code. On the right, we see the refactored version of the app created by our technique. It is shown that the non-interactive elements are actually invisible, or their size is 0, and the interactive elements are stretched since there is no point in having empty space in the GUI. Some buttons are smaller because the code behind them is less complex, and some buttons are larger. It is clear that when we run monkey testing on this version of the app, it is more probable that the monkey interacts with the larger buttons, which leads to the execution of the more complex event handlers or part of the code. Further, there is no empty space, so none of the click events generated by the monkey is wasted. Here is the setting of our experiment. We have repeated the experiment 100 times. Each monkey testing session generated 10k events, and we have computed HC and MC for two sets of methods. The first set is the 42 methods associated with the interactive elements, and the second one is all the 480 methods, 18 methods of the code. The results demonstrate that for both sets of methods, both HC and MC are increased, and HC is increased notably. In other words, when monkey testing is run on the refactored version, the events generated by the monkey have resulted in more method executions, more event handler calls, increasing the chance of code faults being revealed or found. In the left table, we see the top 5 methods that have the highest increase in HC, and in the right table, those with the highest decrease. This shows that the methods that are more complex have executed more in the refactored version compared to the original version, and methods that have less complexity are executed less when monkey testing is performed on the refactored version compared to the original version. And finally, we can conclude by saying that we have proposed an automated technique for GUI layout refactoring of Android apps to improve monkey testing and, in some sense, improve testability of the app. Although the initial evaluation is limited to a case study, but it acknowledges that the technique is promising. We are currently working on improving our technique and implementation to address the wide range of patterns Android developers use in their practice and their codes. Thank you for your attention, and please feel free to ask if you have any questions.